Hello everybody! Today I bring you a video about multimedia course. Specifically, it's a video about transform coding. This kind of coding is used to reduce the spatial redundancy of signals, specifically of pictures and video. With transform coding, we are going to transform the spatial domain into a frequency domain. In this frequency domain, only a few coefficients will contain most of the information in the picture. So instead of having, for instance, an 8x8 block, 8x8 pixels, which are 64 pixels, we will have most of the information maybe in 5 or 6 coefficients, 5 or 6 pixels. So in this case, we have a more compact representation of the information. We have to say that this is mainly a lossless technique. I say mainly because actually we are going to remove the decimal part of numbers because we want to have integer numbers. We want to transform integer numbers, which are the pixels, again into other integer numbers. So we are going to remove the decimal part, and this is the only loss that we are going to have, only the precision that we are going to use. We have many transforms that can be used. For instance, we have the Carhunen-Liouville transform, or we have the discrete Fourier transform, which is very common in signal analysis. We have the discrete cosine transform, or DCT, which is the transform that is going to mainly be used in video and picture coding. But we also have discrete sin transform, Walsh-Hadamard transform. The Hadamard transform is used in newer standards, but in most of video coding standards and picture coding standards, DCT is the transform that is being used. To apply this transform, we are going to divide our picture in blocks, as I said, of 8x8 pixels, mainly 64 pixels, and we are going to use integer arithmetic, as I said. Okay, we are going to remove the decimal part. And as it is said here, DCT, discrete cosine transform, is the transform that is used in most of video and image standards. So from now on, you have to learn this term. You have to learn discrete cosine transform, or DCT, because we are going to use this term in the future. So let's start with Fourier transform. And before the Fourier transform, let's remember something about your math courses. If you remember vector spaces, in vector spaces you have bases. For instance, in a two-dimensional vector space, you have two vectors in the base. So in this case, we have E1 and E2. And you know that any vector can be represented as a weighted sum of the vectors in the base. So if you have V, you know that V can be represented as 4 times E, here 4 times E1, plus 1 time, or once, E2. Because you have here only one E2. So now you know that V can be represented only as the coordinates for 1 using the base, which is composed of E1 and E2. This can be generalized to any number of dimensions, and we know that we can represent V as a weighted sum of V1, V2, Vn. We can represent then V as the coordinates A1, A2, A3, A4, An. Okay? This can be generalized using Hilbert spaces when we have infinite bases. And instead of having vectors, well, they will also be vectors, but instead of having vectors in the real numbers, we will have vectors, for instance, in the polynomials. So we can consider a base which is x raised to 0, x raised to 1, x raised to 2, x raised to 3, etc. So if we have the function e raised to x, the exponential function, we know that we can decompose this using a Taylor series as 1 plus x plus 1/2 of x raised to 2 plus 1/6 of x raised to 3 plus 1 divided by the factorial of I times x raised to I. Or what is the same, the series from 0 to infinite of 1 divided by the factorial of n times x raised to n. But what happens? Maybe we know that we can get a good approximation of the function only with a few components. So originally, okay, we can represent this function, the exponential function, as the infinite vector, which is 1, 1, 1/2, 1/6, and 1 divided by the factorial of I in general, okay, but with an infinite number of terms. However, we know that maybe with a few terms, we can get a good representation in the environment of 0. So what happens if instead of giving an infinite vector, I give a truncated vector only with a few components? So let's see. For instance, here we have the exponential function and the function f of x equals to 1, which is the red one. And okay, we see here that the approximation is not good. It's not good at all. But what happens if I add one more term? If I add one more term, I will have 1 plus x. If I have 1 plus x, I have this approximation. It is not good, but it is better. But what happens if I add a new term? Then I have this one. It's a second degree polynomial. It's quite better than before. And if I add a fourth term, I get something like this. It will depend on where I want my approximation, but if my approximation is in the interval from -1 to 1, I have a good approximation of the exponential function only with 4 terms. So for this interval, instead of giving an infinite vector, I will only give a vector with 4 components. Okay, this can be also translated to other bases. Instead of polynomials, what happens if we use a complex exponential function basis? So instead of x raised to 0, x raised to 1, x raised to 2, etc., I have e raised to something complex, I, n, t. Okay, t is the variable, n is a number depending on the series, and I is the complex unit, the imaginary unit. So this is known as Fourier transform, and we can use Fourier transform to approximate other functions, well, or to obtain a whole representation of other functions. Okay, but we can truncate Fourier transform to get only a good approximation of other functions. But here the key is to know the coefficients here. However, in an image, we know that we don't have an analytical function which models the frame, but instead of that, we have a finite or a discrete set of values, which are the pixels. For instance, I may have the pixel here, which is a 10, here a 20, here a 30, here a 10 again, here 100, usually from 0 to 255 if we have 8 bits, right? So we have an equivalent representation for Fourier transform when using discrete values. So when using discrete values, we have this definition. Here, we don't need an infinite number of elements because we only have, for instance, 10 values. So if we have 10 values, we will also need 10 values to transform the 10 values before, okay? So here again, the key is to know the coefficients here. However, we have a formula to calculate them. It's not that difficult, okay? It's just to replace the values in this formula. You don't have to learn these formulas, and you don't need to calculate them by hand or whatever, okay? But just as an example, we have here a set of 4 points, maybe pixels, which are transformed using the discrete Fourier transform. So you see that 100, 105, 95, and 90 are transformed into, the first value is 97.5, then we have a complex value, and here in the middle, a 0. So what happens here? Okay, first of all, we must notice that we have complex values. This is bad. This is bad because for each of the numbers that we have here, now I need to store two real numbers, the number in the real part and the number in the imaginary part. Okay. But the good point is that if you see, this is a high number, close to 100. Actually, this is the average of all the points by the definition of the transform. Okay, this is the average, and here in the rest of the points, it's like, okay, imagine that now you want to obtain the original values from here. So what it is done is to place the mean value or the average value in all the cells, in all the numbers that we have, and then these numbers will give will say, okay, now the average was 97.5, but this position needs to be a little bit greater, and this position a little bit more. This position needs to be a little bit lower, and this position even a little bit lower than the one before. Okay, so this is what the rest of the coefficients do. Hopefully, but good for us that we don't need to keep all the values. Okay, maybe if we keep only a 0 here, if we replace this with a 0, we will not lose all the information. Even if we only keep this value, we will still have in all the places the mean value. And maybe with two values, I can already know that here I have 100, and here we have a value which is greater than, or sorry, with the first value we can know that the two first values are greater than the average, and the second two values are lower than the average. So maybe if I reconstruct, I can get here 100, 100, and 95, 95. So I already have something only with two coefficients. Okay. Okay. The problem are the complex numbers. We know using Euler's formula that the complex exponential can be divided as a sum of trigonometric functions, of cosines, and sines, being the cosine, the real part, and the sine, the imaginary part. So we have other transform which only uses cosines, so it only keeps the real part, which is the discrete cosine transform. It is here, again, we don't need to know the formula, but if we apply this formula to the previous values, we obtain something like this. Okay, these are the previous values, 100, 105, etc. And now we obtain 195 to 02. Okay, the values are not exactly the same, but the philosophy is still the same. Here we have a value which represents the average of the values that we had before. Okay, it's not exactly the mean value or the average value, but actually it's just a direct transform of a direct scaling from the mean value. So only with the first value we will be able to reconstruct that all the values here are 97.5, and maybe only with these two values, with these two, yes, we will be able to know that here we have greater than the average, and here we have lower than the average. Okay, again, if we add the other terms, we will be able to reconstruct the whole set of values. But only with two values we can get already a good representation. Okay, now if we move to pictures, in pictures we have two-dimensional sets of values, something like this. As I said, we are going to use 8 by 8 pixels. So in this case, what I need is a two-dimensional DCT. We also have the two-dimensional version. It's quite the same, but using two dimensions. Okay, and we will be able to transform a space the space into frequencies. Okay, we will move from an 8 by 8 matrix to another 8 by 8 matrix. In which, well, of course, we can then apply an inverse transform, okay, IDCT, inverse discrete cosine transform. But what happens here is exactly the same that we saw here. That in the first coefficient, we have the mean of all the values. And in the other one, we have like refinements of this value. So if you see, if we focus on this block, which is an eye, okay, always black is close to 0. So here in the center, we have the pupil of the eye, and it's close to 0. And then we have greater values around here and so on. So if we transform these coefficients, we will obtain something like this. We will have here a very important coefficient which will contain the average value of all the coefficients in my block. And it will be a very high value. And then we will have values which are much closer to 0. Okay. Now, in this discrete cosine transform, we have to know that, of course, we can only perform a finite number of operations to derive the numbers, okay, if we apply the formula. But the problem is that we have a cosine in the formula. And the problem is that to calculate the cosine, we need an infinite number of operations, and this is not possible in computers. Okay, so we need to truncate values. Specifically, we are going to truncate to an integer number, as I said before. So we are going to introduce some kind of error, but this error will be very negligible because it will be very small. So it's not a completely lossless technique, but it's almost lossless. It cannot be applied, for instance, to compress documents, but it can be applied to compress pictures or video frames. So after transforming the values, we will have something like this. We will have a very important coefficient here. We will call this coefficient the direct current coefficient, and all the other coefficients will be called alternating current components or coefficients. Okay, so we will have the DC coefficient and AC coefficients. Okay, this coefficient DC is very important. It's the most important coefficient. And now this one is placed always in the top left position of our matrix. And then when we go to the bottom right corner, the coefficients are less and less important. So maybe only keeping the DC and this part of AC coefficients will be enough to represent all the other coefficients that we have here in the original block of pixels. So here again, we have here again the DC, and here we have to know that, as I said, the spatial domain is transformed into the frequency domain. So this is the lowest frequency because it's actually the mean of the block. So if we reconstruct the block only with this, we will not have frequencies, okay? Frequencies in the sense of edges in the block, okay? So here we will have only the mean value. We will have all the values as the same value, okay? So we will have no frequency. Then if I go further from the DC coefficient, then I get higher and higher frequencies, okay? So here I have low frequencies, medium frequencies, and high frequencies. Frequencies in the sense of edges, as I said, okay? So it means that, for instance, if I have a texture which is like all the time sharp, okay, very very sharpened or an edge, I will have a lot of coefficients in this part, okay, and high coefficients in this part. Specifically, horizontal edges are placed in this part of the matrix, vertical edges in this part of the matrix, diagonal edges here, and here we have even higher frequencies. So, for instance, if we move here, we will see how each of the coefficients contributes to the global image. So here we have the mean value, for instance, white, okay? And for instance, imagine that in the middle, exactly in the middle of our block, for instance, like around here, okay, I have a vertical edge. A vertical edge there will be a coefficient here. If I have more vertical edges, I will have more coefficients in this part. And if I have horizontal edge, for instance, here in the middle, okay, I will have a coefficient here. If I have several horizontal edges, I will have more coefficients here. And imagine that if we have an edge here in the diagonal, in the original block, maybe I will have coefficients in this part, okay? We will work about this in the lab session. So let's see what happens if I directly remove most of the terms that I have. So for instance, imagine that I only keep the DC coefficient, the most important coefficient. If for each 64 pixels, I only get one of the values, okay, what I will have is that it's something like this. If you see this image, you will see that it is very blurred, okay, because for each 8 by 8 pixel block, I will only keep one value, the mean value, and I will fill all the positions in that 8 by 8 block with the same value. If I keep three coefficients, the one of the corner and the two adjacent ones, I will something like this. It is still a little bit blurry, but it's not that bad. If I keep six coefficients, I have something like this, which is quite the same visually as this. So here, what we are going to do is to discard some of the terms that are irrelevant, the same as we did when we were removing coefficients to approximate the exponential function. If you remember, we only needed 4 values to approximate the exponential function in the interval that we wanted. So for instance, if we have Lena picture here or Lena image, if we transform the coefficients, we obtain something like this. We cannot see anything here, maybe a little bit of the shapes here, of the edges, sorry. But if we group, for instance, all the DC coefficients and we place them together, we will have something like this. So you will be able to see Lena image in a very low resolution here. Then if I place all the coefficients which are on the right side of the DC coefficient together, and I place them here, okay, if you look at the image very closely, you will see that you can still appreciate Lena edges, the same here, but in the other direction and so on. So we can see that maybe we have all the most important information here, here, and here. Or maybe a little bit more of coefficients, some more coefficients, okay? In general, the farther away a coefficient is from the top left corner, the lower the magnitude of the error will be if we remove this coefficient, okay? The bad part is that, of course, now the coefficients are not in the same range of values, okay? So if we transform pixels from 0 to 255 using 8 bits, we will need 11 bits to represent these values. How this results, of course, in a bit expansion, but it is compensated by the fact that we can have many zero values in the transform coefficients. Let's see an example. We have a picture, a frame of a video here, divided in 8 by 8 blocks. Then I focus on a block. I have the block here. It's an 8 by 8 pixel block here. Okay, I have it here. These are the values of the pixels, ranging from 0 to 255. For instance, I have 168 here, 161, 161, 150, etc. Then I apply a DCT transform. If I apply a DCT transform, what I get is something like this. If you see, I will have a 214 here, and all the other values are much lower. Of course, the farther the value is from the top left corner, the lower the value is. Okay, so we still have values kind of high here, 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 but these values are very low, are very close to zero. So now I apply a quantization. Okay, if you remember, the quantization is to divide these numbers by a given number. The quantization this time will come into as a quantization matrix, because I will divide by lower numbers the more important part of the matrix, and with greater numbers the lowest important part of the matrix. So the DC coefficient will be divided only by 16. However, the coefficient in the opposite corner will be divided by almost 100, and even the coefficients around here will be all of them around 100 in the division. Okay, so what will happen, as I'm again only doing an integer division, I will only get the quotient. So if I divide any of these values between the values in the quantization matrix, I will obtain a lot of zeros. So everything here will be a zero. I will still keep some values here. Here I think I keep a 13 in the DC. Here I keep a 4. Here I keep a 3. And now if I apply a rank length encoder, I will say that, okay, this is a rank length encoder. I will say, okay, I have 0 zeros before 13, 0 zeros before 4, etc. But I will only need to encode these few values instead of encoding 64. Instead of encoding 64, in this case, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think 2 times 11, so 22. I will have to encode 22 values instead of 64. And then these values go through an entropy encoder and a statistical something like Huffman encoder or something like that. And this will be what I will transmit in the video or in the picture. Okay, so all together, again, I have an original block of pixels in the spatial domain. Then I transform the coefficients using the DCT, the discrete cosine transform, and I will obtain something like this with most of the information in this corner and very low values in the rest of the positions. Then I apply a quantization matrix, and in this case, if you check, I only keep one value here, and then this and this. So only 3 values to represent the 64 values that I had before. If I apply a rank length encoder, I will get that I have 0 zeros before 86, I have 0 zeros before -3, and 0 zeros before -6, and then a code indicating that the block is finished. Okay, so if I apply an entropy encoder, a Huffman encoder, or something like that, I will get a transformation of these numbers as a binary bit stream, and that's it. Okay, so if I reconstruct this matrix again from this, then I have to apply an inverse quantization. Okay, if I divided by the quantization matrix before, now I multiply by the numbers in the matrix. If I multiply by the numbers of the matrix, then I reconstruct this inverse quantized coefficients, okay, which should be more or less the same that I had here. What has happened? What has happened is that anything that is 0 here, 0 times whatever is 0. So I cannot reconstruct anything from what it is 0 here. However, having zeros here is good because they will be compressed using the rank length encoder. So here I have everything like as zeros except these three values. Okay, so if you see, I have not lost too much because here we have -1, -2, 1, 2, something like that. So the error is not that bad. And here, okay, I still have errors because here I have 684 and here I have 688 because of course I have removed the decimal part because I had only performed an integral division, but it's not that bad. Now if I apply the inverse DCT, the IDCT, the inverse transform, I will obtain this from this. Okay, so this is again the reconstructed block, and if I check, I had in the original block 75 here, and in the transform one, I have 76. So instead of 75, I have 76. Is my eye able to notice the difference from 65 to 60? Sorry, 75 to 76? I don't think so. So it's in averaging or in global, it's a lossy technique, but the loss comes mainly with the quantization. Okay, the loss doesn't come with the transform. The loss always comes with the quantization. Okay, but in any case, we obtain very similar values to the original ones. So in this other corner, I had 96, and in the reconstructed value, I had again 96. So in this case, we obtain exactly the same value. In other values, we will obtain something like plus less 1 or 2 pixels, which is not that bad. So this is what you have to know about transform coding. I hope that this video has been useful for you, and of course, don't hesitate to ask me any doubt that you have. Thank you very much.